Hello everybody, I hope you're doing well. Welcome back to another video in our Introduction to Calculus playlist. So in the previous video, we went over the concept of continuity and we also got a feel for what limits are. So today in this video, armed with the knowledge of continuity, we're going to try to extract a intuitive yet useful property for us. And this property goes by the name Intermediate Value Theorem, or you guys can call it IVT. So what is the IVT? We're going to start with the concept and intuition and then kind of go through a couple helpful examples to really understand why the IVT is kind of useful, right? So in terms of the concept and intuition, think about it this way. Let's say today was November 11th, right? Or let's say it was November 4th, 1960, right? And you were 5'4", right? And then it becomes November 9th, 1963, and you were 5'10". So what happened? Well, intuitively, from November 4th, 1960 to November 9th, 1963, you went from 5'4" to 5'10". So you essentially grew, right? How much did you grow? Well, you grew by 6 inches, right? Now, one thing that's obvious is you grew from 5'4" to 5'10". But in that growth, what happened? Well, it is true that you would have surpassed 5'6" sometime in between, right? Because you're growing, right? So you went from 5'4" to 5'10". So you couldn't have jumped to 6 foot and then came down to 5'10", right? Assuming that, we don't grow down, right? We grow taller, right? So in the time of November 4th, 1960 to November 9th, 1963, you were 5'6" at some point, right? So 5'6" is in between 5'4" and 5'10". So the 5'6" is like the intermediate value, right? So intermediate value, right? So because you grow in a kind of continuous fashion, well, you plateau at some point, right? But you don't just grow and then suddenly spike up and then come back down, right? So in this case, right, your growth can be approximated as a sort of semi-continuous behavior, right? But 5'6" as the immediate value had to have happened somewhere between November 4th, 1960 to November 9th, 1963, right? So how does all this intuition tie into the intermediate value theorem? Well, we can formalize this exact analogy in terms of functions, right? So how are we going to do that? So let's draw a picture, right? Oops. So let's say we have a graph, right? We have a function that looks something like that, right? I'm going to use different colors to do some labeling. So let's say right here, you were at value a, and this value here is f of a. So the function is f of x, right? And then you have another point b, right? And this point is f of b. Now, let's say that there was some value c right here, right? What is true, right? Well, we know in this case, right, from the looks of the visual, right, this function right here has no discontinuity, right? Right, it has no discontinuity in a less than x less than b. So in the interval a, b. So we know that there's no discontinuity in the interval a and b, right? We also know at a, the value of the function is f of a, and at b, the value of the function is f of b. And we also know that f of a is less than c, which is less than b, right? Or less than or equal to, right? To be more precise. So what is true, right? Well, you know that from a to b, right, there needs to be some x in between, right? Such that, f of that number has to equal c, right? So how do we formalize that? There's some point, say right here, right? There's some point right here. Let's call it x1, right? Where f of x1 must equal c, right? And x1 for a fact is in between a to b, right? Because you just said that at a, the function's value is f of a, and at b, the function's value is f of b. There's continuous behavior from interval a to b, and c is right in between f of a and f of b. So let me fix that small typo right here. So that means that this is enough to guarantee us that there has to be a number, right, in between a and b such that, the function at the number is this value c, right? And notice how I said there has to be a number, right? Doesn't mean that there needs to be one value. There could be other values, right? So like there could be multiple values, right? So imagine if we had a picture that looks something like this, right? Let me move this down. Imagine if we had a scenario like this, right? Or actually, and let's say that this was A. Uh, this was B right here. And then you have, f of A, f of B, and then you have this mystery value right here, which is called K. So you see clearly in this picture, right? You have 3 points, right? Where, there these points right here are where, the function evaluated at these x coordinates 1, 2, and 3 right here equal to K, right? So all this intermediate value theorem is guaranteeing us is if we have the criteria above where the target output we desire, right, is in between two known outputs, and we know that there's continuous behavior between this relevant inputs, right, then that there has to be at least one point, right, where there's an x value in between these two inputs right here, where the function evaluated at those input, right, or inputs is equal to this mystery value c. So this is the exact idea of the intermediate value theorem, and this is a good way to formalize the analogy with the heights and birthdays. Oops. Sorry, I just closed this tab on accident. Okay. So now that we have this established, right, it's important to keep in mind that for the intermediate value theorem, continuity is an absolute requirement. Some people might ask, why is continuity necessary? Well, continuity is necessary because for this to be true, you have to have continuous behavior, right? If we didn't enforce that, right, then we can easily break this graph, right, by having a jump discontinuity, and then, for this mystery value c, you might not be able to find an input that satisfies, right? So if there was no continuity enforced in the intermediate value theorem, then the theorem is just plain wrong, because I could just have a jump discontinuity at the mystery point, right? I can draw a picture of that too. You can try that yourself to convince yourself, but that's why continuity is required, right? And it is a strong condition. Okay, now with that being said, let's go into a couple quick examples for the intermediate value theorem. So the first example should be relatively straightforward. So the first example, I'm just getting it out. Okay, so we have f of x, right? It equals x cubed minus x minus 1. Use IVT to show that there is at least one root in the interval 1, comma 2. Okay, so what are we going to do? We're going to, take the value of the function at the endpoints and then, see if the IVT applies for our case. So we know f of 1 is 1 cubed minus 1, which is -1. And we know that f of 2 is 2 cubed minus 2 minus 1, which is 5. And we know that since this function is cubic polynomial, this function should be continuous. And because 0 is in between -1 and 5, right? So -1 less than or equal to 0 less than or equal to 5, it implies that, there has to be a c in 1 less than or equal to c less than or equal to 2, such that f of c equals 0. So one basic application of the IVT is we can take polynomials and we can kind of identify where a root could exist, right? The IVT doesn't necessarily say the root is exactly at one point. We have to still use algebra to solve it. But the IVT can tell us, oh, this area is where you should search if you want to find a root. So it's pretty helpful for going to find roots of polynomials. Another cool example with the IVT, which is quite interesting, is let's say we had a complicated function and we just, couldn't graph it for some reason, right? Because it's too complicated to say enter in the calculator. But what we do know is from experiments, we have approximate values of the function, right? And we can try solving a basic equation, or at least see where the solution could lie for sanity checks. So let f of x be a continuous function, right? This is important. So let's say that's complicated function we just somehow know is continuous, right? Through, past studies or something, right? And here's the data we have. So we have this table right here. So we know that at 1, the value of the function is -2. The value at 2, it's 3. The value at 3 is 1. The value at 5 is -5. And the value at 8 is 7. So let's say we wanted to find all the places where f of x equals 1/2 for whatever complicated reason, right? How many, what is the least number of solutions to this equation that can exist on this interval? So notice in our complicated function problem, right? Part of finding the solution in our case might be probing to see, okay, in this interval, right, how many solutions could possibly exist at minimum, right? This can help us, sanity check with complicated technology and things like that, right? So in keeping with the spirit, what do we notice? Well, we know f of x has to equal to 1/2, right? This is like the equation we're trying to solve. But what we don't have to know exactly what f of x is, but rather we just have to, look at, the values and how they change, right? So you see right here, right? The one important thing is that f of x is continuous, right? So f of x continuous, very helpful, right? If it wasn't, then we wouldn't necessarily have a guaranteed solution, right? But since f of x is continuous, all we have to do is look at how the value of f of x changes across this interval 1 less than or equal to x less than or equal to 8. So you see from -2 to 3, right? 1/2 lies in between, right? So, but IVT says there's got to be a solution here, right? From 3 to 1, 1/2 is not included in that interval, right? So we can say safely that maybe f of x equals 1/2 might not have a solution in the interval 2 to 3, right? From 1 to -5, 1/2 is included. So by the IVT, the solution might want to exist here, right? And likewise from -5 to 7, 1/2 is included, right? In this output, right? So the solution might exist here, right? So you see here, because the IVT says that, oh, at least one solution must exist, right? Based on like the way the theorem is defined, at minimum, 3 solutions exist on 1 less than or equal to x less than or equal to 8. So the strategy for these type of table problems with the intermediate value theorem is walk through like, successive, order pairs and kind of see, is your target value kind of in between when we look at the outputs, right? Because we don't care about the input, we care about the output value. And using the way the output value changes across successive points, right? So for example, from x equals 1 to x equals 2, and then from x equals 2 to x equals 3, right? We're using that to see, okay, could there be a possible x that meets the criteria we want, namely f of x equals 1/2. So that's a wrap for the intermediate value theorem video. Hopefully this video gives a good summarized definition of the IVT. And like and subscribe. And if you have any questions, please feel free to leave comments. I greatly appreciate it. And have a good rest of your day.